In this week, we are going to talk about another analysis approach. Again, this kind of approach belongs to the brain network analysis. And today's topic is graphic theory. Okay, so sometimes you may find this terminology on the paper. Graphic theoretical network analysis is the topic that we are going to introduce today. So again, please visit my website. And today's topic is the week 14 brain network graph theory. So please download the handout and the materials right here. Okay. And the employed software today will include two new toolbox right here. The very first one is the Gretna. Gretna is one of the GUI MATLAB toolbox that can help you actually finish all the image processing and all the network analysis using this kind of toolbox. And another toolbox called BrainNet Viewer Toolbox. This is actually one of the toolbox that help you to visualize or display the result of the brain network. So this one is actually not an analysis toolbox, but a viewer toolbox, just like the X-ray view to the SPM. So it's just kind of an extended toolbox. Although these two different toolboxes actually developed by the same team from the China. So again, this Gretna toolbox actually using a lot of the functions from the SPM12. So you need to follow this rule again. There is no space or the Chinese character within your file path or file name. Okay, so you need to again make sure that you already have the SPM12, and you need to download this Gretna toolbox from this web link and also the BrainNet Viewer toolbox right here. So in this course, we are still focused on this brain connectivity or brain network analysis. As you may see that actually we spend I think around 4 to 5 weeks focus on this topic, brain activation. So we introduced the SPN, GLN, and also the ALFF or rehome approaches. However, for this topic, we actually spent more than 6 weeks because this kind of the brain connectivity analysis or brain network analysis is very complex, and it actually includes so many different approaches to do so. So today today is the final week that we focus on this issue, brain network analysis right here. And again, I just put this slide right here because today we are again using the data that we acquired from our 3T MRI facility, that we are going to use the racing state fMRI, include the 200 time balance right there. And all other parameters just live right here. If you want, just check these kind of parameters. Okay, so let's focus on the very first part. I'm going to give you the general introduction of the graph theory. What is the basic ideas, or what is the parameters that we can actually calculate it based on this kind of the graph analysis right here. So first of all, we need to understand what kind of the network, what kind of the architecture that our brain actually have. So we take this plot right here as the example. You can see if we assume our brain may have some kind of the linkage or the brain structure like this one. For each circular nodes right here is actually represent one of the brain regions. For example, this is one of the prefrontal regions, and then this one may be the post-central region for the somatosensory function or something else. So you can put each node right here as one of the brain regions. Okay, and the lines right here actually represent the connection between two different brain regions right here. So you can see we can assume if our brain have this kind of the regular connection, or sometimes we say lattice topology, that means each node or each brain region always connected with its neighbor, its closest neighbors right here. So you can see this node may connect to this one and this one, but you can find that there is no long distance that connected to very anatomically separated regions right here. So you have no way to find this kind of the long distance connection right here. You always find this kind of the short connection always connected the neighboring nodes right here. So this is so-called lattice and regular. You can see it have a simple rule, always connected with your neighbor. Okay, this kind of the connection, you can see the cost. Sometimes we say cost is a so-called wiring cost. Just kind of you try to connect all the nodes within this brand. How many wires or how many lines you need to do so. So in this case, actually, you always need to use very short lines or short connection. So we may say that the wiring cost for this kind of the connection, regular or lattice connection, would be very low. Okay. However, we can assume we may have another kind of topology or another kind of a structure of our brand network. We call it random topology. That means there's no rule. There's no common rule that you can say how one brand region or how one node can connect with other nodes right there. So any connection within this kind of brand network actually is exists by random. So you may have chance to have this kind of the short connection, but also you may have the chance to have this kind of the very long distance connection right here. Okay. However, for this kind of the topology, you can say the wiring cost definitely will be higher than this kind of a regular topology, because you now can observe some kinds of the long distance connection right here. So if we compare these two different kind of connection, random and the lattice connection, now we focus not only on the wiring cost, but we focus on another issue, efficiency. No matter what kind of the network that we are discussing, for example, the brand network or internet network, that means the connection between different computers or personal computers right there. This all kind of a situation can form some kind of the network right there. So not only the wiring cost, sometimes we may ask what kind of the connection can bring highest efficiency for this kind of the network. So please guess. Do you think this kind of the regular network may have a higher efficiency, or this one may have the higher efficiency? The answer is very obvious. The right-hand side, the random network may have highest efficiency. Why? Because again, you have the shortcut. When I say shortcut, that means you have this kind of a long distance connection. When I transfer from this node to another one, it just costs one step. I don't need to transfer or pass through other kind of the nodes right here. However, for this case, if I want to go from this node to this node, you need to spend so many different steps right here. Go through so many different lines right here. And as you may say that the direct connection always more efficient than this kind of the indirect or several different connections right here. So you may understand that when we say the basic idea of a network, we always consider these two different things. It's kind of the trade-off. If you want to maintain as low as possible the wiring cost right here, you may sacrifice the efficiency. So this is the very extreme example right here. But another thing is if you just try to connect your brand without any consideration of the cost, you may get a very high efficiency. However, these kind of things may not fulfill any kind of the economic system or biological system, because the connection just consumes so many resources right here. So our human brand network actually located in this kind of the between situation or the middle situation right here. We actually find a very beautiful balance right here. Of course, this kind of a balance is actually developed through 1,000 years evolution right here. So now we have this kind of elegant and beautiful complex topology that we actually have as low as possible but as high as possible efficiency right here. So we have low cost but high efficiency. So you can see this kind of brand network actually may have many different short connection right here. However, for the functional integration purpose, we may have some particular long distance connections right here. For example, you want to integrate the function from the frontal lobe to the parietal lobe, then if you have this kind of direct connection, you can increase or you can improve the efficiency. Okay. So these kind of things that actually you can see there is a very good article that published in Nature Reviews in 2012. Nature Reviews in Neuroscience, okay, in 2012. This Bormore is very important scholar in this field. It just emphasized that actually now people or now researchers believe our brain have this kind of elegant things. Okay, so I put lots of sentences or words right here. Just read it by yourself. But anyway, the most important sentence is this one. Nodes aggregated topologically and anatomically as a module. Sometimes we say module is some kind of the cluster. Now you can say, okay, I can see there is a cluster right here. Okay, and then there may be another cluster right here, and this is another cluster. However, not only you can form this kind of the cluster. Cluster means it's just the anatomically connected. So you may reduce the wiring cost because normally they may close to each other. However, to ensure or to maintain high efficiency, you need some of the high efficient connection, that is a long distance connection. However, you don't do the random connection, but you do a specific way. That, for example, these two modules have to be integrated with each other to form some kind of the high level function of our brain. So we have this kind of connection right here. So this connection is not formed by random, but by purpose. You definitely have some kind of function in this kind of efficiency. Okay, so we can minimize the wiring cost, but by the evolution, now we again maintain the high efficiency in our brain. Before I give you more information about the graph theory or network analysis, first of all, you need to know the definition of a network right here. So we may say that if you want to discuss a network structure, first of all, you need to know what kind of the components are essential for the network structure right here. So two different things you need to memorize. The first thing is nodes. Nodes means the points, just like we display right here. This is the points right here. And of course, these nodes or the points right here actually represent a key anatomical location in our brain. So sometimes we say it's just kind of the cortical regions. We focus on the gray matter, okay? And the edges right here is actually the connection. However, for the graphic display, sometimes we say with node and edges we can form the network. Okay, so edges right here, you can just put another alternative term, just like the connections right here. To form this kind or to estimate the kinds of the edges in our brain, actually you can employ the different imaging techniques. You can estimate this by using the structural imaging, or you can using some kind of the fiber stratigraphy approach that we can actually reconstruct the structural connection or the fiber bundles or neuronal axons, that you can use this kind of a DSI, DTI, or even some transneuronal tracer. You can do so. You can just find out what is the structural or anatomical connection right here. However, in this course, we mainly focus on this topic, functional connectivity. You can definitely use the fMRI that we introduced in several weeks before, and also you can apply the other kind of approach, such as the EEG and the magnetic measurement for the MEG right here. You can anyway just try to find out the statistical correlation or statistical dependency between the signals extracted from two different brain regions. So we can somehow just estimate this kind of the functional connectivity between different brain regions. So we can form this kind of the invisible. You cannot really see this, but you can estimate the dependency between the signals extracted from two different brain regions. So we say this is a functional edges, or sometimes the functional connectivity right here. So we can say actually network is composed of several nodes and the edges between nodes right there. So you can see this is two examples right here. This is the structural brain network. You can see the authors still use the straight line represent the structural connectivity. However, if you see some kind of the stratigraphy before, you may see the actual neural fiber within our brain is actually curves, or sometimes it may have some kind of the just a very complex connection, not the straight line right there. However, this is kind of the graphic representation, so also just use again the straight line to represent these kind of things. And on your right hand side is the functional brand network. And then you can see now we use two different color, red and blue, because normally when we calculate the Pearson correlation coefficient, we have positive number and the negative number. So we can use red represent the positive number and the blue color to represent these negative connections right there. So either way, you can construct this kind of the brand network, or sometimes we say connectivity matrix right there. Okay, so you can see you may have a different value for different network. However, they all represent the edges with this kind of network. And to build up a network, they have at least two essential steps that you need to do. After you estimate or you obtain this kind of the functional connectivity matrix on hand, what you need to do, two essential steps right here. The first of things, we may apply the threshold right here. So you can see this is the original network matrix right here. However, with some kind of assumption that we may say the connectivity strength or connectivity coefficient, if the connectivity coefficient too low, we may say we don't have the strong evidence to claim this kind of the connectivity really exists. So we may use the thresholding that we may get rid of the value that actually lower than a certain specific value right there. So normally for the Pearson correlation coefficient, we may use 0.3 or 0.4 as the threshold, because normally the 0.3 or 0.4 may correlate with the p-value around 0.05 if you have the sample size around 30 or 25 or something. So this is a common threshold that we may use. However, you may find out that in some papers or some studies, the threshold can be one of the variant. That means they may test every kind of the networks that you can apply the several different thresholds from 0.01, 0.05, 0.1, 0.15, along to the 0.4 or 0.5 or something. So you can just try to adjust the different threshold value right there, and just try to observe how brand network may change along with this kind of a different threshold right here. Okay, so this diagram right here actually depicts the idea about how threshold can change the formation or the appearance of the network right here. So you can see this is the original network. You may have so many different connections right here. However, now we use the thickness of the line or the width of the line to represent the strength of the connection. If we have the thinner line right here or the wider line right here, that means we have the strong connections right here. Okay, so now if we apply the threshold to get rid of all the thin line right here, that means the edges with small or weak connections right there, then you can see we will have a cleaner, more cleaner network right here, that there is no weak connection displayed right here. Okay, so this is the very first step, threshold. Help us to focus on the most important connections within this network. And then this step may be optional. We can either binarize our network or just leave all the original values right here. So you can see for this one, sometimes we say this is the weighted network. That means we preserve all the original value. You may have the 0.3, 0.35, 0.36. You have the actual values right here. However, for the binarized network right here, we may say we just want to check whether the connection exists or not. It's either 1 or 0 problem right here, or none problem right here. So you can see for this diagram right here, you still can see the thickness may differ between different connections right here. However, after binarization process right here, you may find out that actually all the line become same width. Okay, and the network or the matrix right here will only leave the value to be 1 or 0 right here. Okay, so this is binarized. I don't care. I care no more about the weighting or the connection strength right here. I only focus on whether the connection exists or not. Okay, so I think this is two essential steps, but will definitely be the key steps that you try to construct any network or the subsequent network analysis right here. Okay. And for our brain, we already know that our brain actually have this kind of elegant structure that we have sufficient efficiency, but as well as possible, the wiring cost very big. And actually, we have a special term right here called small world architecture. Small world architecture right here. Small world architecture, again, is actually located between regular or lattice structure and the random structure right here. However, this special term is actually developed by I think it's a social scientist. Originally, they tried to understand what is the distance between people. For example, if you live in the east coast of the U.S., you try to reach out for someone actually lived in the west coast of the U.S. So in that era, people can only try to connect with each other using the handwritten letter. You don't have the email, you don't have the Facebook. So in that era, one of the social scientists tried to find out how many steps or how many later you need to transfer from people to people, then finally can reach out the people that you want to know from another side of the US. So the result of the experiment actually tell you the number. Actually, 6 is the magic number. We sometimes call it 6 separation. That actually, you want to know anyone that you originally didn't know, you can just try to send one letter to someone you know and ask him to send someone that may have the highest possibility to know that guy. And this kind of experience actually tell you that in average, 6 separation, that you need to transfer your letter for 6 times, then this letter may eventually go to the person that you want to know. So based on these kind of things, even US is that large. But however, this world is not that large. So the final conclusion is actually we live in this kind of the small world that only have the 6 separation. However, nowadays we have email, we have Facebook, we have Twitter. So nowadays this magic number reduced to around 2.3 or 2.8. I'm a little bit forget about the number. However, it's reduced from 6 to 2. So if you want to know even the Trump, you just send an email to someone you may know. For example, I may have a old friend now working in US. I just send the email to him and try to ask him, maybe you know the Trump or not. Just please transfer my email to someone else. And you may find out that now the separation is around 2 point something. Okay. So this small world architecture is an alternative term for the brain network, because our brain network actually fulfill the criteria for this small world. What is the criteria for the small world? High local clustering. That means you have the cluster or module in our brain that you segregate the brain regions or segregate the brain regions within small anatomical locations right there. This is what we call the local segregation. So normally when you say the motor network within our brain, we may say primary motor cortex that actually located in the precentral gyrus, and a little bit forward you can see they have the supplementary motor area still close with the primary motor region. Even the frontal eye field again is pretty close to the posterior part of the frontal lobe and also the anterior part of the parietal lobe right there. So we can say this kind of things is so-called the local segregation. We have high local clustering or high local segregation right here. And again, our brain, however, still have the low separation when we consider 2 distant regions. For example, the frontal region and the occipital region. We still have the low separation because we have the, again, long distance connection right there. Okay, so this kind of things, for example, you have the superior frontal parietal fasciculus or inferior frontal occipital fasciculus or the inferior frontal occipital connections right here. So that is why we still have the low separation within our brain. So our brain have this kind of the very good structure right there. We have the very strong local segregation, but sometimes we have the long distance connection right there. So now you can know our brain not only very efficient, low cost, but also fulfill the structure, so-called the small world architecture right there. So this kind of turn actually already be observed. This kind of property already be observed within several different networks. Not only within the brain network, even the social network, internet network, or even the biological system. Okay, we can observe these kind of things. So now I try to give you 4 examples about how can we measure the network properties right here. Now we need to base on this kind of a graph theory. Graph theory is actually an approach that we can use some kind of the quantitative values to quantify, for example, the efficiency of the network or even the connection strength within a network. So we take these 4 parameters for the example right here. Of course, we have so many different orders parameters that I will list it in one of the slides later. But we take these 4, this more straightforward 4 parameters right here. Sometimes we say this is the graphical properties or topological properties right here. Okay. So now we take this small network or just this network as the example right here. We actually only have the 9 nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9. We only have 9 nodes. And the possible edges or connections between these nodes right here. You can see that we don't really have all the mutual connection between every single node right here, but we just have the specific connection or edges right here. Okay, so now we may focus on either specific node, we call local property. We can focus on specific node, for example, the node 9 right here. Or we can somehow calculate the global properties right here. That means after calculating all the local values right here, we can take the average number right here. That means we try to give a summarized value, single value, to claim what kind of property for this kind of network. Okay, so this is the global properties right here. So we start from this one. We take the node 9 as the example. So we start from this one, degree. Degree by definition is actually the number of the neighbors that this specific node has right here. So you can see for degree 9 right here, how many nodes within this network actually directly connected with this node 9 right here. So you can see direct connection may be observed between 1, 2, 3, and node 8 between node 9 right here. Okay. But for other nodes right here, they don't have the direct connection. They may pass through other node to connect it with the node 9. However, only these 4 nodes right here may have the direct connection. So we may claim the degree of node 9 is actually equals 4 right here. Okay, 4 neighbors or 4 nodes connected with this node 9. And the strength again is just kind of the averaged or the mean value of the correlation coefficient right here. So for our case, you may say the connection between for this edge is actually may have the Pearson correlation coefficient about 0.7, and this one 0.3, 0.4, and 0.6. So strength for this node is actually take the average number for all the direct connected regions right here. So you just take the average. So the strength for this node 9 is actually 0.4 right here. And the clustering coefficient is actually, we try to estimate the segregation degree between the directly connected neighbors right here. So again, we take the node 9 as the example. Now we only consider neighbor. So we can see the neighbors are 1, 2, 3, 8. We don't consider the connection to node 9, but actually we want to know the connection between these 4 nodes right here. So you can see actually all the possible connection may be this one, this one, this one, this one, and also the diagonal between 1 and 3, and also 2 and 8 right here. So actually for all the possible connection, we have 6 potential edges right here. However, in this network, in reality, we lack the connection between A and 10, A and 2 right here, right? So we only have the 5 connection. So the actual clustering coefficient is 5 divided by 6 right here. 6 is all the possible connection, but 5 is the actual connection that you can observe between these 4 neighbors right here. Okay, so the clustering coefficient right here would be 0.83. You can see if I have all the connection, for example, we also have the connection between 2 and A, the clustering coefficient would be 1. So you can see the clustering coefficient is actually the probability that the probability of the connection between all the neighboring nodes right here. So if this is the 0, that means you don't have the very good clustering property between your neighbors. However, if you have 1, that means full connected situation right there. Okay. The final one is the shortest path length, or sometimes we say separation. Okay. Separation means the minimal steps that you can start from one node to another node that you want to go. So for example, the node from 9 to 6, what is the separation? Well, what is the shortest path length? Of course, it's 2, because you can go to A, and then shortest way is directly go to 6. Of course, you can go to A, then go to 7, go to 6. You can take 3 steps. However, the separation right here aims for the shortest path length. So right here, we say the separation right here is 2. You only take 2 steps to the node 6 right here. So you can imagine that actually the efficiency of one network is actually like the reverse value of this separation. If I can have as small or as less as possible separation you can have, of course you may have a high efficiency right here. Okay. So this is the 4 essential numbers you can calculate for each node, or you can, after the calculation for each node, you can just average all the numbers to get the global parameters to represent the degree or strength or clustering coefficient or separation for this whole network right here. Okay, so this is a general idea about actually we try to understand the property for each node and for the whole network. And this 4 is the most famous and the most popular parameters that you definitely need to learn. And actually, why network analysis is that important? Because, of course, we can simply focus on the direct connection. But sometimes, if you only focus on direct connection, you may miss some hidden information or some high-level information. We take this network as an example. If now I say a disease may disrupt or destroy one of the edge or one of the connection. Now you can imagine if the disease attacked the edge or the connection between node 3 and node 4, the influence may be very different from if this disease attacked or destroyed the connection between node 3 and node 9. Why? Because for this connection, this only destroy or only affect the connection for the node 4. However, if you destroy this connection, you may find out all the connection from whole bunch of the node connected with 3 will disappear. So you may now understand that actually why sometimes we may discuss which node is most important or which edge is most important within this network. And to do so, only if you can estimate the full network, then you can answer which edge or which node is that important. For example, node 9 may be very important because if you want to connect this module with this module, you definitely need to go through node 9. However, if you lose one of the brain region, for example, the node 4, the effect may be very, very little because it's kind of the marginal node or marginal brain region that may put too much influence on this network right here. So network analysis is that important because it's bring you another level. Now you can understand why one disease affect one region or one connection may cause so much different result. Okay, this is because the connection may be very different, depends on the brain network structure right there. Okay, so this is just one of the example. Just try to inspire you that to think about why I need the network analysis right there. And there's a very important paper published in 2010 right there, published in Neuroimaging. Actually, this is more like a technical paper that focus on all the brand network properties. It also give you the MATLAB code, the source code that you can use it as what you want to do, and also interpret or just explain all the meaning behind all these kind of properties. So this paper is that important. Right now, you can see only 9 years is already accumulated over 5,000 citations. It's crazy things. It's very, very important. So nowadays, every brand network analysis need to cite this paper, and all the toolbox need to cite this paper. Sometimes we will say if you have a paper, have the citation over 100 times, you need to celebrate it. But this paper have 5,000. So this is very important. Okay, even the toolbox. Gretna and the BrandNet, the toolbox also employed the source code from this paper. So again, this is an essential paper that you want to know the interpretation or you want to find the source code on hand. This brand cognitive toolbox come from this paper, and this is a website that you can visit. You can download all the MATLAB source code. Okay, so you can construct your own toolbox or perform the network analysis. If you don't want to use a GUI to do so, you can just use all the source code from this brand connectivity toolbox right here. So right here, I try to list as many as possible, but however, it's not the full list right here. You can see there are actually so many different properties to measure a network. So we only mentioned the degree, strength, the separation, and also the clustering coefficient right here. However, still there are so many different parameters right here. I don't have time to go through one by one. I can just tell you where the resource is. You just try to read the paper, okay? And then try to use this paper as the tool or as the basis. Try to figure out how other papers may use this kind of technique to interpret their data or try to investigate how one of the disease may change your brain structure. Okay, so right now I just try to give you a brief introduction. I hope that after this introduction you have the general idea why network analysis is that important and what we can do with the brain network analysis right here.